Welcome to Discrete Mathematics. Today we are going to explore the minimal forms of polynomials. Imagine giving someone directions to a store. You could give them a long, winding route, or you could just tell them it is right behind them. Both get you to the same place, but one is vastly simpler. In digital logic, we do exactly the same thing with Boolean expressions. Before we can minimize anything, we need to understand the building blocks of a Boolean polynomial. A polynomial here is just a logical expression. It is built from literals, which are single variables or their exact opposites, such as x or not x. When we multiply these literals together, we form what is called a term, like x times y. Understanding these pieces is essential because our goal is to reduce them as much as mathematically possible. Now that we know the pieces, what does it mean for a polynomial to be in its minimal form? A Boolean polynomial reaches its minimal sum of products form under two strict conditions. First, there is no other equivalent expression that uses fewer terms. Second, among all expressions with that lowest number of terms, none uses fewer total literals. In plain English, we have squeezed the expression down so tightly that removing even one more letter would completely change the actual meaning of the formula. To reach this minimal form, we rely on core rules of Boolean algebra. The most powerful tool is the adjacency theorem. Conceptually, if a result is true when y is true and also true when y is false, then y does not actually matter. In this formula, x and y are Boolean variables holding values of 0 or 1, and y prime is the exact opposite of y. Because y must be either 0 or 1, one of those two terms will always just be x, allowing us to drop the y entirely. Another critical rule we use is the absorption law. This rule states that if a condition x is already true, adding an extra option of x and y does not give us any new information. The larger term xy is completely absorbed by the simpler term x. Physically, as x changes from 0 to 1, the entire expression perfectly mirrors x, making the y completely irrelevant. This is a fantastic way to quickly eliminate bulky terms from our polynomials. Let us see how these rules work in practice. We are given a Boolean polynomial f with 3 terms and 6 literals, and we want to reduce it. First, we use a special trick. We duplicate the term xy. In Boolean logic, adding a state to itself changes nothing, so this is perfectly legal. Next, we rearrange and group the terms using parentheses. We pair the first xy with xy prime and the second xy with x prime y. This sets us up perfectly to factor out common variables. Continuing with our grouped terms, we factor out the common variable x from the first group and y from the second group. Now we apply the complement law. Any variable added to its exact opposite always equals 1 because one of them is guaranteed to be true. So the complex variables inside the parentheses become 1s. Finally, multiplying by 1 leaves just the variables themselves. Our final minimal form is simply x plus y. What started as a messy 3-term expression is now a basic OR operation. To truly understand why we just did that math, look at this diagram. On the left is the physical circuit for our original unsimplified polynomial. It requires multiple logic gates, specifically 3 AND gates and an OR gate to process the inputs. On the right, after our mathematical minimization, the exact same logical truth is achieved with just one single OR gate. This visual proves how algebraic simplification directly translates to building simpler, more efficient physical hardware. Now let us tackle a larger problem. We need to find the minimal form of a polynomial p with 3 variables, x, y, and z. It currently has 9 literals. We look at the first 2 terms and see they share the exact same xy part. We factor xy out to the front, leaving z plus z prime inside the parentheses. According to the complement law, z plus z prime must equal 1. We substitute the number 1, completely eliminating the variable z from this part of the equation. Multiplying by 1 simplifies our first term to just xy. Our expression is now much shorter, but we must check if it can be reduced further. Both remaining terms contain the variable y. We factor y out of both terms, isolating x plus x prime z inside the parentheses. Here we use a special Boolean rule called the redundancy law, which states that x plus x prime z simplifies directly to x plus z. The complex inner expression is now replaced by a simple OR operation. For our final step, we simply distribute the variable y back inside the parentheses to get our expression back into the standard sum of products form. This gives us our final minimal polynomial, xy plus yz. We have successfully reduced a complex 3-term, 9-literal expression down to a simple 2-term, 4-literal expression. This is the absolute simplest way to write the original logical instructions, meaning the resulting physical circuit will be as efficient as possible. You might wonder why we spend so much time factoring and applying laws. Finding the minimal form of a polynomial is the absolute backbone of modern computer engineering. Every Boolean polynomial directly translates to a physical circuit made of microscopic logic gates etched into a silicon microchip. If an engineer uses a long, unsimplified polynomial, the resulting circuit requires unnecessary physical gates. These consume more electricity, generate dangerous heat, and slow down the computer. Minimization ensures the processor is as fast, cheap, and energy efficient as physically possible. Let us review our key takeaways. The minimal form of a Boolean polynomial is its most compact, efficient representation that preserves the exact same logical truth. By applying algebraic rules like the adjacency theorem and the absorption law, we can factor out redundancies and strip away unnecessary complexity. Ultimately, this mathematical simplification directly translates to building better, faster, and cheaper digital technology in the real world. You now have the tools to look at a chaotic set of logical rules and distill them down to their purest essence.